panelists introduce themselves to put the questions back in. That should still be working, hopefully now. And then we can use those to read them out. Oh, actually, I see that. No, sorry, they're still there. The questions are still there. That's great. So continue putting them in and voting them. For some reason, they didn't show up for a second for me, but actually they're still there. That's perfect. Okay, so Anqi, do you want to briefly say something?
Sure. Hi, everyone. Hope most people have seen me yesterday. So yesterday I talked about how important model fitting is for me. And more precisely speaking, it is GLM, not just a very simple linear model, right? Because in most of the real world scenario, especially in neuroscience, people deal with nonlinear model fitting and with very complex noise like Poisson, Bernoulli, and so forth. So yeah, so GLM is basically kind of my bread and butter thing. If you want to do model fitting in neuroscience application, similar to Memming, right? You analyze the relation between neural signal with sensory data, with behavior output, with basically all possible external information. And you can use GLM to do either encoding or decoding as we introduced in the tutorial. So I would say I mean, there are certainly more complex models like neural network or whatever, right? But GLM is always a very good starting point, at least for you to start to analyze neural data and to analyze the relation between neural data and the external world. And I believe most of people here or who have done some data analysis with neuroscience data must know that GLM is very fundamental kind of model people usually start with, or maybe you also end up with GLM. But yeah, I just want to say, like, I personally have a lot of experience play around with all kinds of GLM, with all kinds of neural data, and yeah, and that's why it's really important, and it's very necessary to be introduced at this early stage of the summer school. Hope you all have also already learned something and enjoyed that.
Thank you, Anqi. Cristina.
I'm going to do the super short version now. So I'm an assistant professor in neuroscience and data science at NYU. We do quite a bit of work using GLMs more recently in the context of data sets where we have recordings for brain regions where historically we don't have a very good idea what the neurons care about. And in the context of tasks where the animal is doing something really complicated, where it's not just a few really stereotypical kind of features that are going on in the outside world that the neurons are responding to, but complex, many features happening at the same time that have complex coordination structure between them. So one example is monkeys navigating in virtual reality, trying to find shoes. We also have some more reinforcement learning tasks in rodent, where the animals are deciding how long to wait for a probabilistic reward that may or may not come. So in this context, we use GLMs as a starting point and generalization of GLMs for making things more complicated for ourselves, because we always want to make things more complicated for ourselves.
Great, thank you so much. Okay, I think we're ready for questions. So the first question is by Kyle Poe. Could you provide an intuitive perspective on the reason L2 and L1 regularization combat overfitting, and which are to be preferred in what circumstances? Are there cases where higher order LP norms would be favored? The supremum norm question mark?
Who wants to go?
Anyone who feels like it.
I feel like I've said my piece already in the intro, so I would repeat very much the same kind of argument that I made there. So maybe somebody can add something new to the story.
Sure, I'll take a stab. I mean, this is a like 4-part question here. So I would say that the intuitive explanation for L1 and L2 regularization fighting overfitting is that it's trying to shrink the weights towards 0. right? So basically, the evidence from the data is trying to push the weights to a certain point, while the regularizer is trying to pull it down to 0. And if the evidence from the data is strong enough, then it will fight and stay large. While if it's weak evidence, then it will be shrunk and have less effect on the model. So that's how it would fight overfitting. And basically, models with lots of zeros in these kind of GLM type models are the ones that have no effect, meaning these are simpler models. So effectively, it has less parameters, right? Those parameters that are close to 0 have less effect, meaning these are the simpler models. So by argument of Occam's razor, simpler models perhaps better in generalization. But of course, that might not be the case. But in practice, this is mostly the case. So that's the first part. And the second part of the question, where you're asking the higher order LP norms would be favored for regularization. I have not encountered such a case. I don't know if Anqi or Cristina has an opinion on this.
I've seen people use LP norm when P is like 1.2, 1.5, or when P is even infinite, like L infinite norm, right, where you are minimizing, the norm is the maximum or the kind of the superiorm of the whole set. I've seen something like doing that. I feel like it's a more conservative norm where you don't really aggressively smash all the weights. You're only regularizing the maximum one, which is not very often or commonly used indeed in neuroscience. I've seen people play around different way of LP norm in pure machine learning regime, but because different norm have different kind of ball, right? And for example, the L1 norm is this rectangular, and L2 norm is unit ball, and different norm has this kind of unit ball shape that results in different properties or for the whole like weight vectors. So I don't have very strong intuition like when you should use LP norm when P is very large or it's like the superior norm. But for L1 and L2, I think what Memming has explained is kind of the basic rule or like the basic intuition people would use for L1 or L2. So
there's also the part of the question where which one is preferred, L1 versus L2, in which situation? Oh. So in most cases, L2 would be the go-to norm, and L1 is preferable if you have more sparser results, more interpretable results, or if you expect the output to be very sparse, the parameters to be very sparse.
Yeah, I can just use an example in fMRI, if people are familiar with fMRI analysis, which you usually try to decode scalar information like the external stimuli or something from the whole brain neural pixels or neural voxels. In that case, you don't really expect the whole brain neural voxels to fire in a specific event. Only very sparse regions of the brain are very correlated with the task. So in that case, people use a lot the L1 penalty to smash down the weights corresponding to most of the regions in the brain, but try to figure out which region fare the most or is the most correlated with the specific task. That's like a scenario where people use a lot of L1 rather than L2.
Cristina, do you want to add something to that, or are you happy?
I mean, like I agree. You first start with L2 if that it looks like lots of the weights are relatively small, or you have a priori reason that L1 might be the better solution. Anqi's example is one. This the naturalistic tasks that we're playing with are also of this kind, where there are lots of things going on, but an individual neuron will not care about all of them. We expect it to care about a small fraction of the things that are going on in the world in the context of this particular task. So we use L1 a lot in that setup as well. You can also combine them if you want.
Great, thank you so much. Okay, the next question is by Miguel. It's again a long question, so bear with me, please. And maybe you can read it at the same time, it might be easier for you. A logistic regression works based on a Bernoulli probability density function, essentially a coin flip. But say you don't only have two options, for example, left or right, but you have more, so left, right, up, down, no go. What kind of decoding GLM can use neural data to predict behaviors like this?
It's a relatively simple generalization of the binomial of the Bernoulli distribution. So they use a categorical distribution for the observation model, and it works kind of the same as the Bernoulli. So it's just like, instead of having two outcomes of your flip coin, you get 5 or whatever we had. But it works very much the same way.
Like rolling dice.
Right,
Yes.
and if you want to look it up, it's called the multinomial logistic regression.
Mm-hmm.
Yeah. Okay, that was an easy one. Joao Runyo asks, could you possibly use L1 logistic regression as a feature selection method, even if you end up using other linear model to fit your data? How would this compare to other feature selection methods?
That's a tough one.
Yeah.
I mean, there are many, many feature selection methods. L1 is just one of them. But in the context of regression, L1 is probably preferred by a lot of people because it's fast and simple. A lot of the other feature selection methods, like when you're iteratively adding one feature at a time, or combinatorially searching for it, those are possibly more expensive to do. So I would say L1 is convenient, it's fast to fit, so why not try it first?
I think the question was once you sort of figure out what features you want to zero out, do you want to refit the resulting model or not? I would say not, but right.
I'm actually confused by the question. It seems like the question he want to ask is, if I'm using a linear regression model, but I want to use an L1 logistic regression as a feature selection. That's how I perceive the question, which I feel is quite confusing. Maybe I understand that wrong, but what I would want to say is always use L1 with the model you try to fit. I mean, because when you come up with a model to fit the data, that means that is the model that would be the most appropriate model or interpreted model that you hope to learn some knowledge from the data. Then you stick to that model and you use L1 together with that model to do feature selection, because it's possible that you use L1 with logistic to find some feature, but this feature might not be really related to the task you try to do with the true model you want to fit. I'm not sure. I mean, because this question,
the likelihood, that sounds bad. If that's what we were planning to do, that sounds bad.
Yeah, basically don't try to use L1 logistic just purely as a feature selection tool. And after you select the feature, you use the feature to fit your model. I wouldn't suggest doing that, because usually when people say feature selection, it's not just this feature is good or not. It's more like whether this feature is related to the data. So you need to, yeah, I think what is more important is figure out the model you try to fit, and then combine feature selection with your model fitting, not as 2 steps. I don't know. That's a legit way of answering this question. But yeah.
I think one of what we said was probably what they wanted.
I don't know exactly what was intended, but we've covered our bases, I think.
Okay.
Right. Okay. Next question is by Ricardo Diaz. What's the most important thing to have in mind while choosing a GLM to solve a problem? That's a very general question, but I think it's actually a very good question. So what are sort of like the, you know, the different steps that you should not forget about and the different red flags that you might want to keep in mind or something like that?
Yeah, so I'm sticking to my table. First of all, think about what your what your data is like. Then decide on an observation model, and then decide what else you want to add in terms of bells and whistles. Sometimes maybe the feature spaces and how do you want to parameterize your features might be not obvious in the context of your task. And there, I guess it's a little bit of a black art. There's no obvious answer. You think about which versions are more relevant in terms of interpretation, maybe.
I think interpretation is indeed key. And to get a good interpretation, you have to design your GLMs, deciding which variables are input and output, and having a particular question that you want to answer from, you want to ask the model to tell you. You can fit GLMs to anything, as long as you have lots of numbers, you can just fit it. But if that would be meaningless if you don't have a good question in mind. And a good question in this case would be all, either a regression or a classification problem type models. So deciding if your question fits in this framework or not, I think should be the first step.
So you brought something up that I think is very important, which is sort of like the format of the data that you have. Maybe we can comment a little bit on what's the importance of formatting your data correctly in terms of pre-processing potentially, or transforming the data in certain ways. Like, if you have, let's say you have position data, do you first derive velocity and acceleration signals and then do a GLM versus not? What's the best way of approaching this?
It depends on what you want to do with it, I guess. I mean, with some things, it's sort of like whitening some features and stuff like that might be convenient for certain purposes, but I don't think there's a general rule of how you would want to pre-process your feature space. I don't know. Do you have opinions?
It's sort of an art. It's if you want to choose different basis functions to represent it, if you want to pre-process it in different formats, those could change the results dramatically. It could make your model, perform very well versus, you don't get anything out of it. If your actual variable was acceleration that mattered, but you put in location. So that's critically important to find the right features, right? And some nonlinear transformation of the features. If the features are linearly transformed, GLMs can handle that perfectly fine. But if you do need to find these nonlinear features first before you plug it into the GLM, that requires you to have a good insight of how they might be related, right? So prior knowledge, prior scientific knowledge comes into play, and also visualizing first, right? Plot your data first before you try to fit them. See if there's any trend at all. That would be my advice.
Great. Okay, next question is a very detailed question about tutorial 1 from Jane Huang. In an LNP model, what is the exact relationship between firing rate, the lambda, and y, so the variable y? If y equals lambda put through a Poisson distribution, why were both y hat and rate divided by lambda calculated as an exponential function, so exponential of x times theta, I guess, in the tutorial exercises? Does anyone know?
I can briefly say something. So first we want to know is lambda, the firing rate, is a deterministic parameter for the Poisson mass function, and y is a random variable with stochasticity that can be described or can be generated from a Poisson distribution. So there are like different things. So for people who might be more familiar with Gaussian, this firing rate lambda is like the mean of the Gaussian, and y would be the random variable that follows a Gaussian distribution. So they're not the same thing. And if y equals lambda if y is equal to lambda put through a Poisson distribution, y were both y hat. Actually, I don't know what is rate over lambda calculated as exponential. Not quite sure about the later part of the question.
So maybe is Jane in the audience? Do you want to explain?
Yeah, sorry. The first part of your question actually, or your answer actually answered my question very well. I think I just got caught up in the details of the code itself. But yeah, I understand better now. I think I was just confused as to why it seemed to me that the noise was excluded from the code. But I think that's a separate issue than the conceptual question, which you've answered for me totally. So thank you. Great,
thanks. Awesome. This is actually kind of useful for in the Zoom that we can. It's much easier to call people in to briefly clarify than it is in Crowdcast. Okay, the next question is by Igor Zverev. And the question is, how precisely did we choose nonlinear functions for our, so how precisely did we choose nonlinear functions for our GLMs? Like the exponential for the sigmoid function. Can you explain it again? I missed some details during the tutorial. More generally, what's the usual approach for choosing this nonlinear function?
I can do that. Once you've chosen the likelihood function, that has some natural parameters. So the Poisson has this lambda parameter, for instance, or and these parameters of this distribution have some constraints on them. So lambda needs to be a positive value because it's a mean of counts, and those counts are positive numbers, and the average of them needs to be positive. So whatever nonlinearity you choose needs to give you at the output something that looks like a lambda. So that in this case, it's positive. It's positively valued as a good and can be arbitrarily large. So exponential gives you that. You could come up with some other nonlinear function that gives you that, but the exponential is the most obvious one. It's also mathematically convenient for certain purposes if you actually pair it together with the expression that gives you the Poisson distribution. Because there's a log there and some things cancel out and the math becomes simpler. But in general, the minimal constraint on the nonlinearity is to give you parameters in the form that satisfy the minimal constraints that the parameters of the likelihood distribution needs to satisfy. So if they need to be positive, if they need to be between 0 and 1, like it's the case for the Bernoulli, then you need something that squashes everything between 0 and 1, and so on. So sigmoids do that. Some other nonlinearities of the same kind do the same thing. So,
maybe I can add a little bit to that. So for the using the exponential for Poisson GLM, of course, is mathematically beautiful, but also it's known as the canonical link function. It's statistically it makes some sense in this mathematical form. But as Cristina was saying, you do have a freedom of choosing more broad classes of nonlinearity there, and people do use different nonlinearities. One thing to keep in mind is if you choose a very complicated nonlinearity, the benefit of GLM having a unique convex optimization problem and giving you the optimal solution can break. So there are certain subclasses that are preferable. So if you look at the literature, I think many of the Paninsky or Pillow papers will have these constraints. Like it has to be log concave and convex nonlinearity, and widely used is soft rec and the rectified linear are also. I guess rectified linear is not in this class.
Oh, but you get the smooth rectified linear.
Yeah, so there are some tricks to do this, but keep in mind that if you choose arbitrary one, you might break it. So you need to be careful.
Yeah, simple is best usually. Like for sigmoids, if it gives you numbers between 0 and 1, exactly how the squiggles work, it doesn't particularly matter, honestly. So keeping those expressions as simple as possible, it seems like a sane thing to do. There are very rarely good reasons to make the nonlinearities much more complicated, I would say. I've never seen it in practice.
There are examples of that happening in spiking, right? So if some neurons, you did the GLM analysis, you know the neuron likes certain features, but some neurons will have like a suppression effect if it's too strong, right? If it's up to some point, it'll stronger and stronger feature will increase your firing rate, but if it's extremely large, it suddenly starts decreasing its firing rate. It will not continuously increase. So some people do these kind of post hoc analysis of projecting your input data into the filters or the parameters of your GLM and try to recover what's the optimal nonlinearities and try to interpret what these neurons do physiologically. So there are options and there are cases where that might be necessary, but of course optimization wise those are more difficult.
Yeah. No, so that's true, that if you really want to you could improve the data dictate.
So Alex Ivanov in the chat asked a follow-up question: does the function have to be differentiable? So for example, the ReLU function is not. Is that the idea?
I mean, if you can choose a differentiable function, why not? I mean, if you want to do ReLU, you can do soft ReLU, right? I mean, the performance usually is not going to be that different, but it's better. It's a better function to use. I mean, from my personal experience, I use ReLU a lot, but I don't really use the ReLU. I use the soft version of the ReLU. I think especially, yeah, no matter you're using TensorFlow or PyTorch or C, people always prefer differentiable functions over non-differentiable functions, unless it's like, it's very essential, like no other functions can replace that.
I mean, this goes into the hairy details of, optimization. ReLU is, in fact, very popular these days in general machine learning.
Oh, that's true.
But they ignore the fact that it's not differentiable.
Well, if it's sub-differentiable, there are good optimizers to exploit, of course. But I think that's out of the focus of today's one. I think there are other days that will deal with this much better in depth.
Yeah. So the next question is sort of a foreshadowing question, I guess, by Xijiang Han. What is the relationship between L1 regularization and dimensionality reduction? So dimensionality reduction, they will only learn about tomorrow. So keep that in mind maybe when answering the question.
It might be maybe a better question to ask tomorrow.
It might be a better question to ask tomorrow, unless you want to already have a little bit of a quick conversation about that.
My understanding about dimensionality reduction using plain language is you just reduce the number of features in some way. It's a very general concept. So if you want to say, then L1 could be a possible way of reducing the dimensionality by just directly throwing away features. But usually people don't really call L1 as dimensionality reduction method. But yeah, you can think of, usually dimensionality reduction means you apply some linear or nonlinear transformation of your feature space so that you can reduce the feature space to smaller dimensions. If you learn PCA tomorrow, that's like a small eigenspace. It doesn't have to be the feature space, like the orientation, contrast, or whatever you see from the data. It could be the eigenspace of the feature space, which is a linear transformation of that. So, but yeah, I mean, people don't really call there's a relation between, but you can think of L1 as a specific way of doing the dimensionality reduction. I'm not sure that's true or not. Maybe people have other opinions.
Yeah, I think there's a comment in the chat from Matt Laporte, who says that, but in general, you're not throwing entire features out when you do dimensionality reduction, right? You only compress.
Yeah,
And
yeah.
you're selecting sort of like the main features, but we leave the other ones in. You don't just throw them away typically.
Yeah.
I guess
it's better covered tomorrow. It's very hard to
potentially at least.
Not 100%, right? That's possible. Like the main direction you select is orthogonal to some feature. In that case, you're essentially throwing that feature away. So that's very complex. But yeah, I think.
I mean,
I would suggest not thinking L1 as a dimensionality reduction.
Yeah, I would also not do that.
I generally agree. I mean, I just wanted to add on to this because we're talking about GLMs. GLMs generally are not thought of as dimensionality reduction. Dimensionality reduction, usually you don't have, independent and dependent variables. Although there are cases where you are interested in reducing the dimensionality of my high dimensional input data, I'm only interested in the subspace somewhere hidden here that's related to my other variable. In that case, perhaps GLM kind of framework would be useful. And there's a more fancy machine learning type of dimensionality reduction framework where you can call the autoencoders, where you can encode your input data to some feature space and then decode back to your original input space. And if you think of that as a regression to yourself, so you're regressing X to X itself, then perhaps this makes more sense. But this is a little advanced, perhaps.
This sounds too
This is even beyond the course. I don't think they're going to introduce autoencoder at all in this.
Actually, autoencoder will be the last day.
Oh, will be.
Excellent.
Okay.
So this is a preview then.
Yeah, long preview.
Okay.
Keep that in mind for the rest of the course until the last day.
Ask some GLM questions to the autoencoder section.
Yeah. Yeah,
but you can ask the dimensionality reduction already after learning PCA. I feel like autoencoder is too advanced. Maybe talking about PCA first and then autoencoder would be more natural.
I will say no more.
Great. Okay, we have a long question from Alex Sheffield. At the end of the tutorials, we are told it is unwise to overinterpret the weights of our GLM. Okay. However, L1 regularization makes this very tempting with the parsimonious model it results in. If we can't interpret the weights after L1 regularization anymore, any more than after L2 regularization, why would we use it? Is it even better to be using a model that is essentially throwing out data than, is it better using a model throwing out data than a model that carries meaningful information?
So interpretability is tricky, right? So I agree that whenever you have like individual feature dimensions that are thrown to zero via L1 regularization or just for other reasons, that kind of says, statistically speaking, that this response or this output does not care about that feature. So that bit is kind of interpretable in that sense. Where it gets dangerous, I think, sometimes is when you try to attribute individual parameters in these models to biophysical reality. So I think one of the most common examples that I've encountered is when you talk about functional couplings. So when you have these filters that track interactions between neuron A and neuron B. There, the temptation is to say that corresponds to a synapse in the circuit that these neurons talk to each other. And practically, that's very rarely the case. So it's a statistical dependency between these two, but it doesn't tell you that this is necessarily that this is a direct interaction at the biophysical level. So in that sense, those parameters become dangerous to overinterpret.
I think that
the fitting out of model class stuff, or does somebody else want to say something about that?
I just want to add up a little bit. Like, I think there's always a long-term debate between about interpretation of these kind of statistical models in neuroscience. I think the interpretation of the model and the interpretation of the parameter you learn in neuroscience is kind of a little bit two things. You can interpret the model well, as Cristina said, but whether the parameter is really biologically plausible or related to the neural problem has to be carefully thought. It is not very, so I think that's probably what it means by don't over-interpret the weights.
Yeah, so I think is that there's also something that if your data doesn't really come from that model class, so you're going to do an as good a job as you can in fitting the parameters of that model to your data, but the resulting parameters will not necessarily capture the true structure of the data. That's a more tricky one, because that's sort of like a statistical interpretation issue in a way. But that's also sort of like possibly too abstract for this crowd to discuss in detail.
I have a cautionary tale for the L1 regularization. So often the time is that you have some small amount of data and you're fitting your model, and L1 regularizer chosen through cross-validation would say, oh, prune 25% of your weights. Those are not very useful within this cross-validation. But of course that pruning is might be only because you have not enough data, right? If you have strong signal and you have a lot of data, maybe those weights that were pruned out were actually there and they were not zero. So if you're thinking about interpreting these zeroed out weights as like a hypothesis test, like, oh, is this weight important or not? That's a dangerous route. So it's useful for predictive power, it's useful for regularizing your model, but you have to be careful in terms of making that decision. Oh no, these weights are not important. These neurons don't care about this signal, right? That black and white decision, you may want to be careful when you're using L1 to make that decision.
So the statement that you would make is that in the context of this data set that we have, there's no evidence for this particular feature driving this response, something like that. Which it would be true, but it might change for a different data set or for a different amount of data.
Yeah, in many cases, even the same data, if the same problem, when you get data from different sessions and you fit the same L1, you might learn different features. So that's because the data is very noisy, or like the SNR is very low, and that then you find, for example, this neuron is helpful in this session, but it's not really selected in the other session. So for a specific model to the session, you can interpret that, but then what you learn across sessions might give you very contradict information. So that is purely the data issue, not really because this neuron is biologically related to the behavior in this session, but not the other. So that's always happened, like in my experience.
Okay, I think we might want to take one more question before we wrap up, so that the students can get a bit of a break before the project works. So there's a question by Randall. Our examples of encoding decoding models dealt with experiments where you have neural data on one hand and some other features on the other, and I'm going to summarize the rest. Can you also do this by trying to relate the activity of two brain areas, for example, together? And if so, is that encoding, decoding, or both?
Yes, the first one. So you can regress the activity of some neurons onto the other neurons. That was the second class of interesting neuroscience questions that we had at the very beginning of the intro. I didn't call that either encoding or decoding because that sounds like a complicated terminological argument. So we typically call that functional couplings. So we give them a special name. It's about interactions between neurons to neurons, and then sort of you don't need to call them encoders or decoders.
I would say the word encoding and decoding really only means something because you're relating something that you know the meaning of to the thing that you don't know the meaning of, right? So in the case where you're trying to regress some external variables like velocity or visual information, then that you know the information and you're trying to find that representation in the neural space. But if you have two neural data which you don't know the code of, I think it might be difficult to use the terminology encoding decoding. You might just call them some statistical dependence, some temporal structures that you found, but not necessarily, you know, which direction is encoding and which direction is decoding. Is, yeah, probably doesn't make too much sense.
Yeah.
Great. Thank you so much for those insights. I encourage the students that ask questions that have not been answered, again, to copy them over into the Neurostars forum. That way you might get some answers there. And then I would like to give Memming and Anqi and Cristina the opportunity to maybe say a few last wise words, any recommendations regarding GLMs or regarding anything else that you would like to share. Cristina, do you want to start?
Sure. So we were a little bit depressed in this kind of, we overemphasize the negative parts and the limitations and the cautionary tales and all that, but these things are actually extremely useful despite of all those comments. So, they're fundamental, we use them a lot, they give us a lot of insights, although they need to come with their little footnotes in terms of interpretation. And whatever more sophisticated things you're going to build on top, they're very likely going to recycle a lot of the building blocks that you've seen today.
Thank you, Cristina. Anqi.
Yeah, sure. I think maybe I can combine yesterday's topic and today's topic together. So yes, these 2 days tutorial topic are mainly about model fitting, where you try to regress one thing to the other. So it's more like a supervised setting. And the supervised learning itself is a very basic, but also very important concept in general machine learning. In the future tutorial, you might learn dimensionality reduction, dynamic model, and all that, but those are more complex, like learning problem. But supervised learning is always where we should start, but it's also very, very important. So I would suggest for people who don't really fully understand model fitting yesterday or GLM today, spend a little bit time to try to finish the exercise and try to understand. I know like people complain it's probably too much work to do and very intense, but I really think it's very important as a supervised learning kind of setting. And it's a very useful tool to analyze neural data. But yeah, like we really suggest people spend time to crank it and really understand that well. And you will benefit a lot by understanding that and analyzing the neural data. So yeah, that's my.
And again, this is not something that you'd have to do like right now, tonight, or you know, pulling an all-nighter or something like that, or over the weekend. But this is something that is generally important. Model fitting is in general a super important aspect of all of our work. And if this is something that you know, that you'd like to dive a little deeper in, then that would be a very useful thing to do, because it's so globally and broadly applicable to pretty much everything we do, from simple linear regression to very complicated modeling. And of course that can wait till after Neuromatch Academy. You don't have to stress out right now. But that is a general recommendation that I would also have, is that if there's one thing you want to learn and deepen later on, that would be the right thing to do. Okay, sorry, Memming.
Well, that's a great wisdom. I mean, yeah, so definitely very fundamental in many aspects. And a lot of the more complicated models actually build on top of the GLM framework. And you've learned the 3 types of GLMs, but that's not all the GLMs. There are many more GLMs that are out there. One of them, the multinomial, multiple class logistic regression. Yeah, so there are many fancy methods out there, and you should also look at those as well as GLMs, and always keep in mind that these basic GLMs do capture a lot of the statistical relations. A lot of the interesting parts are captured by these guys. So always try GLMs first, and most importantly, you should have fun while doing science.
Awesome. Thank you so much, everyone. Thank you so much for the panel, Memming, Anqi, and Cristina, for joining us and offering your insight and your time to all of us. This was very enjoyable, and I hope we'll see you all soon. Take care, everyone.
Yeah, bye. Thanks, Gunnar.